Okay, so we've looked at straight line graphs, we've looked at quadratic graphs. It's now time to look at the other weird and wonderful graphs that you can be asked about on the GCSE. So the first one of these is the cubic graph, and cubic just refers to obviously the highest power of x. If we have an x cubed in it, that is a cubic graph. Bear in mind that not all cube numbers are positive, so if you were to do -2 cubed, we go -2 times -2 times -2, that actually give you -8. It's a minus times a minus times a minus. Could you try and fill in the values for these graphs, see what you come up with, and unpause when you're ready. In 3, 2, 1. Okay, so the values I got for the first graph would look something like this. Now if we plot these out, we've obviously got 0, 0 in the middle. We've got 1, 1 and 1 minus 1. And then we've got 2, and it goes up massively and rapidly up to 8 and -2 down to -8. Now if we plot that all together, what we get if we fill in the gaps is a sort of up and down system. So we start low, we end high. This is an example of a positive cubic, as you can tell from the fact it's just x cubed. But that's the general shape that you want to know. Okay, what about B? 5 minus x cubed. So we are going to do, let's do 0 first. 5 minus 0 is 5. 5 minus 1 is 4. 5 minus 2 cubed. So 5 minus 8 is -3. And then what else have we got? This will go to 6 because it'll be 5 minus -1, and that'll go to 13. So we might not be able to fit all of the graph on, but let's see what we can fit on. So at 2, we're down to -3. At 1, we're up to 4. At 0, up to 5. At -1, up to 6. And then at -2, let's just say for scale's sake, 7, 8, 9, 10, 11, 12, we're somewhere up here. So the graph would look something like that. It's roughly like a flipped around version of the first thing we did, and that's because this is a negative cubic, and you can tell that because it has a minus in front of the x cubed. Okay, what about our last one? So when you're calculating, say, this box here, you're going to have to go -3 cubed minus 4 times -3. That's how you type it in. That'll give us -27 plus 12, so that'll go to -15. And then if we repeat the process, we'll get these values. And they look very funky indeed. We have the value 0 appear 3 times. So what the hell is this going to look like? Well, let's have a look. So we can certainly fill in 0, 0. 0, 0. We can fill in 1 minus 3, so that goes down to here. 2, 0, goes back up. -1, 3. -2, 0. And then -3 goes all the way down to 15. Now that's going to be somewhere in this sort of region. And 315 is going to be somewhere up here. So what would that actually all go together and make? Well, we'd start really low with our cubic. And let's try and do this even better. There we go. We'd then pop up to 3. We go back down to 0, down to -3, back up to 0, and then finally all the way up to the top. So let's draw that even better as well. There we go, perfect. That is a cubic with a little bit of a twist. It's a positive cubic again. You can tell from the fact it's positive x cubed. And we still have the thing that it starts low and ends up high, but it's got this little wiggle in the middle. Now, at A level and things like that, you'd be expected to do a little bit more on cubics, but that's all we really need to know, that we can plot them and draw them. So here's a couple of exam questions that I was able to find on cubics, if you want to have a go, and unpause when you're ready to look at the answers. In 3, 2, 1. So what we would get for this is we have -1 as our missing value on the table. Then we want to plot the values. So these are a little bit hard to see, so we'll just have to go roughly speaking there. We've got -1, -1. We've got -2, -9. We've got 0, 1, 1, 3, and 2, 11. Now we know this is a positive cubic because it's an x cubed, and we can sort of see the shape that it's going to have. Remember, you try and join these together with a curve, and that's exactly the problem with graph 2. Criticize the graph of y equals x cubed. The only thing I can think of is that the lines should be curved. All the values are correct, they just need to be joined, with some sort of gradient going on. Okay, that's cubics. So what's next? Exponentials. Now exponentials are graphs where we have a power of x. They're also pretty popular in the news at the moment with all the COVID graphs showing exponential growth. So this is a good one to try and wrap your head around. Right, I'd like you to try and substitute these values in, see what you get, and draw the resultant graph. I'm going to show you the values and my graph for A when you unpause. So have a go and unpause in 3, 2, 1. So those are the values that I got. Now I found it very useful to put these in terms of decimals. It made it easier to read. Let's see what we actually get. So our first one is going to be at 0, 1, and we've got 1, 2, and 2, 4, and 3, 8, which will just about fit on it, and then 4, 16 will be somewhere up here. We've also got -1/2, so that's still positive. -2 1/4, -3 1/8, and we can see that it's getting smaller and smaller, but it never actually gets to 0. It's kind of halving each time. So if we put that all together and make a graph, then an exponential curve looks something like this. You can see there you've got very, very rapid growth. If you put that next to a quadratic or a cubic, this will be climbing way higher and way faster. Okay, try the same thing with 0.6 to the x. I'll come back once you've had a go in 3, 2, 1. So those are the values that I got. Now the only thing I'll point out is that they always have this in common, that when you have a power of 0, you're obviously always going to get an answer of 1. So what does this look like when we plot it? Well, we've got the 0, 1 point, as we just mentioned. By the time we get across to 1, we're down to 0.6. By the time we get across to 2, we're down to 0.36, and then 0.216, and then 0.1296. It's kind of doing the opposite of what the previous graph did, isn't it? So the last graph was getting very small towards the left. This graph is getting very small over towards the right. Whereas on the left, by the time we get up to -1, we're up to 1.6. -2, we're up to 2.78. -3, we're up to 4.63. -4, we're up to 7.72. And we can see that same pattern that we saw before, where the growth is getting more and more rapid, which is what defines an exponential graph. So what can we say in terms of like rules to know for an exponential? So number one, we can say they always have what we say a y-intercept of 1. And that's because anything to the power of 0 is 1. And the other thing we can say is that they are always positive. So you can see the graphs are always above the x-axis. That's generally true for an exponential. Okay, so quite hard to find some exam questions for these, but this is what I found. Here we go. Here's Nick's terrible sketch of a graph of 0.5 to the power of x. Make one criticism of his sketch. And this is the fact, basically. It is always positive, but this should be 1. It should always go through the y-axis at 1, because 0.5 to the 0 would be 1. Here's the other one I could find, and I'd like you to actually have a go at this one first. Pause the video, and come back in 3, 2, 1. Okay, so this was an end of paper question, and what we've got to recognize is that if we have values for x and y, we can substitute them into an equation and they should be true, because if it says it's on the curve, that means that x is 3 and y equals 1/64 works in this equation. So let's try that. If we use x equals 3 and y equals 1/64, then we can say y equals k to the x. We could say that 1/64 equals k cubed. Yeah, you see how we sub that in? Now if we wanted to find what k was, we could just cube root both sides of this equation, and we could find that k is a quarter. So we've got this second point where it says show that this point lies on the curve. We've basically got to show it's true. So we know that this is y equals k to the power of x. We know this is y equals a quarter to the power of x because we worked that out. if we sub in x equals a half and y equals a half into that, we get that a half equals a quarter to the power of a half. And if you type that into your calculator, you can show it's true. Or another way you could do it, if you weren't happy with that, is a power of a half means a square root. And the square root of a fraction means the top needs to get square rooted and the bottom needs to get square rooted. So the square root of a quarter is indeed 1/2. But just saying, getting to this tick mark and saying you've checked it, that would be enough. Okay, let's look at some even rarer graphs. This one is called a reciprocal graph. And it's y equals 1 over x. So we're going to divide 1 by whatever the x value is. Try and fill some values in, try and see what curve you get. You might want to unpause before you're finally drawing it, but you can definitely write the points down. I will show you what I have in 3, 2, 1. Okay, so those are the values I've got, and the kind of important one is this error in the middle. If you try and do 1 divided by 0, it just doesn't go. You'll get an answer of maths error on your calculator. That means that point doesn't exist. It means there is nowhere where x is 0 that we have our graph. So let's plot the points that do exist. So we'll first off go all the way across to -5 and up to, and down rather, to -0.2. All the way across to -1 and down to -1. -0.5 will go down to -2. -0.2 will go down to -5. I have picked these points for a reason, by the way. I'm not just doing random values. 0.2 goes up to 5. 0.5 goes up to 2. 1 goes up to 1. And 5 goes up to 0.2. So what would this look like? Well, we can kind of see it's getting smaller and smaller as the value of x gets more and more negative. And as it's getting towards 0, we can see it's going down. And it's not going to cross this line because that would suggest it actually has a value of 0. What kind of happens is the graph kind of just disappears away into infinity down there, and then it jumps back from a really high number once it reaches there. That's a bit of a mystical way of phrasing it, but well, that's the graph you should get. Okay, so that's a reciprocal graph. And the last 3 graphs that we want to introduce are the trig graphs. Now we'll talk more about these when we get to graph transformations. For now, these are just things to go away and learn the general shapes of. So we've got y equals sin x, cos x, and tan x. And you can see these are all between 0 and 360 degrees. And that's generally what GCSE wants you to be aware of. So what do they look like in those gaps? So we can see there's a couple of different shapes here, and I have a very tortured beach analogy that I think can help. So if you want to remember the shape of a sine, you remember it's the shape of a little sine wave. Okay, which actually is something that's used in music, to be fair, which refers to this graph. We're still at the beach. For cos, what shape have we got there? Cos is a bucket. Starts up, goes down, goes back up. And then we've got sine waves, we've got cos bucket, and finally we've got tan lines. So tan just sort of goes up and down all over the place. Now, we'll talk more about that when we get to graph transformations, but for now it's just worth knowing that trig graphs exist, and that's roughly what they look like. Okay, cheers. That was the weird graphs.